This problem asks about the vibrations of the air inside a drainage pipe. Let's go ahead and prepare by taking a look at the physical situation, okay? So here's the situation. I have a drainage pipe, and it's 30 meters long. But here's something that's equally important. Both ends of the pipe are open. So this is an open tube. Now, wind blowing across one end causes the air inside to vibrate. What will happen is this will vibrate at the frequencies of the standing waves of an open tube. And we know what those look like. Okay, both ends of the tube are open. And so each end is going to be at atmospheric pressure. And so thinking of sound as a pressure wave, we have a node at each end. Okay? So my m equals 1 mode looks like this. My m equals 2 mode looks like so. My m equals 3 mode looks like this. And so on. Now we know the frequencies of the different modes too. The frequency of mode M is just equal to m times v over 2L. I need the speed of sound, and I also need the length of the tube. Okay, so here's my physical situation. It's going to depend upon, frequencies depend upon the speed of sound, the length of the tube, and also the mode number. So we have everything we need to know to start doing some solving, and let's do that. Let's go ahead and solve. And we'll solve for these three pieces in turn. Now for starters, we're looking for this. If the speed of sound is 340 meters per second, what will be the fundamental frequency of the air vibration in this pipe? Well, part A is asking for F1. That's the fundamental frequency. Well, that's just equal to 1 times V over 2L. Now notice, L is given to three significant figures. V is given to three significant figures as well. So we're going to express our result to three significant figures. So it's V over 2L. And what I get for F1 is 5.6666, et cetera, et cetera, et cetera. I'm going to give my answer as 5.67 hertz. Okay, 5.67 hertz. That's my answer for the frequency of mode m equals 1, which is the fundamental frequency. Now part B asks for the frequency of the lowest harmonic that would be audible to the human ear. Now, the frequencies that are audible to the human ear are greater than 20 hertz. 20 hertz is what we're told is the cutoff for hearing, and that's about right, okay? So we're looking for the lowest possible mode that's greater than 20 hertz. Which mode is that? That's what we're trying to figure out. Well, notice this. FM is equal to m times v over 2L. So FM is just equal to m times F1. We know what F1 is 5.666, et cetera, et cetera, et cetera. So we can work out what the different modes are. Okay, F1 is equal to 5.667 hertz, keeping an extra significant figure. F2 is double that, which is 11.33 hertz. F3 is triple that, which is 17 hertz. Okay, F4 is 22.7 hertz. Oh, and check it out, this number is greater than 20. And so the frequency of the first harmonic that a person can hear is going to be F4. That's 22.7 hertz. That's the first harmonic that is actually audible. Now part C asks for this. What will happen to the frequency in the later afternoon as the air begins to cool? Now let's look at our relationship right here. Okay? The frequency is proportional to V over 2L. Well, the length of the tube doesn't change. But as the air begins to cool, the velocity of sound goes down. The speed of sound decreases. So if the speed decreases, the frequency of all the different harmonics decrease as well. So as a consequence, the frequency of the tube that it sounds at will be lower later in the afternoon as the air begins to cool. Finally, let's take a look at our results and see if this makes sense. Okay, the frequencies are quite low, but the tube is quite long. Okay, and when we've seen problems having to do with like organ pipes, and we looked at resonances for other kinds of like tubes, the lengths for things that produce audible sounds are significantly less than this. So expect something less than the frequency your ears can hear. We also know that the frequency varies with the speed, and if the speed is lower, the frequency will be lower as well. And you know, this is kind of a typical length if you have kind of like long tubes for like drainage. You don't hear these things singing as you drive by. And so you expect that the frequencies are lower than you can hear. That's in fact what we find. And so as our assessment, we can say that this does match our ideas about how the world works.